Okay, thanks, yes, for the kind introduction. And welcome, everybody, and congratulations for making it to day 2. Good, okay. So this part is really going to, the purpose of this part is really to give you an overview of everything that's happening in this space, which means that we will be talking about a lot of different things. And unfortunately, we don't really have time to go into a lot of detail on everything. If you do have any questions, then feel free to interrupt me, and I'm happy to answer those. And then we will go into a little bit more detail in the second part of this, just before lunch, when we have a look at some exercises for a specific area here. I also want to say that usually I'm not as grumpy as in the picture on the website, and I am still jet-lagged, so anything that is incorrect that I say, that is because of the jet lag, obviously. Okay. So let's get started. Here's the big picture first. If you have done any kind of constraint programming, you will know that this is not entirely straightforward, right? And you probably got that impression yesterday already because, well, there's lots of different things you can do, and depending on how you do it, then you want to do this and you want to do that. So the difficulty is not really doing it as such, it's doing it in the right way, in quotes. And of course, what the right way is really depends on what exactly you want to do and in what context you want to do this. Like, for example, are you interested in solving really, really large problems? And are you running out of memory? Or are you interested in solving something in, well, quotes, real time, which we heard about yesterday, and then you need to make sure that your problems are, that you can tackle them in real time, and that your solver can solve them in a reasonably small amount of time. And what all of this essentially boils down to is that you have lots and lots of lots and lots of possibilities of doing this. How do you want to model it? How do you then want to solve it, et cetera, et cetera? And really what this is that you have to search through this space. And you can do this either by saying that, well, hey, I've been doing this for a decade or more, so I know what I'm doing, or you can rely on a machine to do this for you. I tend to do the latter because I'm not that good at the former. In particular, I try something and then, oh, actually that didn't work. Okay, so if you're like me, then this talk is for you. And the point of all of this is really to lower the threshold of adoption, so that even if you don't have like a decade of experience in constraint programming and machine learning and all these kinds of things, you can use these techniques, and you can also achieve maybe not quite state-of-the-art performance, but at least you can get reasonably close to it, and you can solve the problems that you're interested in. So that's where we're going to start with this, and that kind of is what ties everything that I'm going to talk about together, and the different aspects of this. In particular, what we're not really going to do is look inside what, for example, a constraint solver does. These are techniques that sit on top of this, and the great advantage of that is that you can really apply them to anything that kind of works in this way. So in particular, as T has mentioned already, you can also apply this in the machine learning context, where you can essentially use the same kind of stuff to achieve similar performance improvements, and again, lower the threshold of adoption. So, you want to use machine learning, and you kind of have a rough understanding what it is, but you don't know the details of how to get the best performance in a particular case. You can use the same kind of techniques to get good performance there. And as it turns out, you can apply these even in completely different contexts. So I've been doing work with collaborators that I will not talk about, in material science, where we've, again, applied really exactly the same kind of techniques to a very different problem, but because we set it up in exactly the same way, we can do this, and we can, again, get good results. If you're interested in this, I'm happy to talk more about this afterwards. Okay, so let me motivate this a little bit, going back to, well, almost 10 years now. Here's a picture that, if you have done a lot of empirical stuff in constraint programming, will look familiar. So we have two axes here, two different approaches. Don't worry about what exactly these mean. We'll get into a little bit more detail on that later. Two different approaches for solving particular constraint problems. And each cross here in this plot is one constraint problem. We have the performances on the x and y axes. So what this means is that if we have a point on the diagonal that is pointed out there for you in a dashed line, that means that both of these approaches have exactly the same performance. In other words, it doesn't really matter which one we use. Either one is fine, well, maybe not fine, but at least there's nothing to be gained by switching from one to the other. As you can see, most of the points are not on the diagonal. In particular, they are very, very far away from the diagonal. And that means that there's a large performance difference between those two approaches. So really what we want to do is, for each one of those crosses, choose the best approach. And that in some cases can get us literally orders of magnitude difference. Not by doing anything to the problem, not by implementing a more fancy solver or anything like that, really just by choosing between the two things that we have available here and making that choice intelligently. So this is really what we essentially want to do. Given a problem, we want to find the best way of solving it. And here you can see that this does make a lot of difference in practice. Like I said, orders of magnitude in some cases. Now, of course, it doesn't always look like this, but in a lot of cases it does. Here's a similar picture where we now compare. This is for a SAT solver for some work that was done even before 10 years ago, where we compare the default configuration, so you just run it out of the box without tweaking anything, to a configuration that is optimized for the particular set of instances that we're interested in here. And again, you can see that there are large performance differences. So diagonal is, again, the line of equal performance, as in the default configuration and the optimized configuration are giving us exactly the same. And you can see that for the larger instances, for larger problem instances that take longer to solve, we are very far away from this diagonal. In particular, we found an optimized configuration that is able to solve these larger problems essentially the same amount of time as the not so large ones, whereas the default configuration increases in time there. So and you might notice the, hang on, there we go. This weird bit here where there is no difference, and if you look at the scales for this, you will see that this is to about roughly 1 second. This is simply because we don't care about these very, very small instances. We want something that works well on large instances. If it solves in a second or less, do we really care whether we can optimize this? Well, you know, in specific contexts we might. In this context here, we don't. So this is not kind of a limitation of the method. This is just the way in which this particular optimization process was set up, where we care about the hard instances, those here, that with the optimized configuration we can solve in, oh, what is that, about 3-ish seconds on a log scale here, whereas the default configuration 10 to the 4 seconds, so orders of magnitude more. That's what we care about. That's what we focused on here. But in principle, we could certainly do that for these areas here as well. And you'll have a closer look at that in the exercise in the second part. OK, so hopefully you feel sufficiently motivated now on a Tuesday morning for this. So here's again the common theme. This is really the general family of approaches here is called meta-algorithmics, because we are not changing the actual algorithms, but we're doing something at the meta level. We're sitting on top of the algorithm and then deciding, oh, OK, in this particular case, I want to use this one here, and here I want to optimize performance and do some tuning and that kind of stuff. So all of this works without really looking into what, for example, a constraint solver does, and in particular, it works without having to modify these constraint solvers. So this is, again, so you are able to do this without being an expert in constraint solving technology and needing, like, you know, a PhD and 10 years of experience, and then you can really optimize this. This is something that you can just do. Yes, so you don't need a particular deep understanding of what happens inside this black box of a constraint solver, for example. And again, the advantage of this is that this means we can apply this to all kinds of black boxes. So is the black box a constraint solver or a machine learning system or a system to produce a particular new type of material? It really doesn't matter. In the end, we can apply all the same kinds of techniques. And so the fundamental idea here is that we want to essentially adapt these existing approaches automatically. We want to tailor them to a particular problem instances rather than developing new ones, because in particular in constraint programming, this field has been around for a while. So there's tons and tons of approaches out there already. And really, if we're going to start developing our own, chances are that we will simply reinvent something that has already been done. So let's not do that, and rather try to find a way of using existing stuff better automatically. And the automatically is with the caveat of more or less. So some approaches work more automatically and some less automatically, and we'll get a little bit into that. OK, so here's the simplest formulation of the problem that we want to solve, the algorithm section problem. Going back to the mid-70s, given a problem, choose the best algorithm to solve it, or in general, more generally, the best approach to solve it. And you have all done this, right? I mean, not even just limited to constraint programming and stuff like this, but if you think back to, for example, an algorithms and data structures class, then you did exactly the same thing there. You were given a particular problem to solve, and you wanted to come up or find the best algorithm to solve it. Here's a slightly more sophisticated formulation of the same thing that applies in the context of automated parameter tuning. So we essentially want to find a parameter setting searching over a space of possible parameter settings that maximizes without loss of generality. So if you want to minimize, it works in exactly the same way. The performance that we observe of the parameterized algorithm on a particular set of input data. So that could be, for example, that I want to solve a couple of Belgian-type problems with sauces and beers, and I want to do this as quickly as possible. Or I want to do some job shop scheduling, and I want to do this in a real-time context where I also have constraints on the memory that is available. So I want to, on one hand, be able to solve it quickly, and on the other hand, I want to solve it to not crash because it runs out of memory. So this is really a very, very general setting, and again, not limited to constraint programming. So exactly the same thing applies to things like machine learning, except there we usually talk about minimizing the loss instead of maximizing the performance, but really they're two sides of the same coin. So you can really phrase one in terms of the other. And this is also a generalization of the algorithm section problem that I showed you on the previous slide, where the main difference is really that for the algorithm section problem, we have a couple of more or less discrete choices, and we don't necessarily know how they relate to each other. Like, you have a choice of two different constraint solvers, and you really have no idea what in detail the differences are between those. I mean, you could maybe do a diff on the source code, but that's not really going to tell you much, right? Whereas for the automated parameter tuning problem, we have more nuanced information because we have a single algorithm, and we know that this is parameterized, for example, by a choice of heuristic, let's say a variable ordering heuristic, and you have at least a rough idea of what smallest domain first is compared to some activity-based heuristic or something along those lines. So you have roughly a better understanding of what's going on underneath the hood there and what the meaning of those different parameter settings is. But again, you don't in particular, you don't have the first principles knowledge that tells you that on this particular problem, you really want to use smallest domain first. On this other problem, you obviously want to use this other heuristic. We don't have that kind of knowledge, which is why we need to tackle all of these things as a black box problem, where essentially what we want to do is intelligently explore this space of possibilities here, lambda, and then choose something that gives us good performance in this particular case. So this is obviously a really, really general problem, and you find this in the literature in all kinds of different contexts. Unfortunately, you also find all kinds of different terminologies and notations and all that kind of stuff. So, your lambda might not be called lambda, but maybe it's a theta in a particular paper or something like that. This can be somewhat confusing. But again, because this is a really, really general problem, it crops up in all kinds of different contexts, and unfortunately, people use all kinds of different terminology. But in the end, it really all comes down to this: algorithm selection and automated parameter tuning. Okay, so let's dive a little bit into algorithm selection first, and what is involved in doing that, and then we will come back to automated parameter tuning, which we will also have a look at for the exercises after the coffee break. So what we're assuming for algorithm selection is that we, first of all, have a choice. If we only have one algorithm, then there's obviously not a whole lot we can do. In particular, if this algorithm is not parameterized, well, here's your one choice for solving the problem. Your choice is, do you want to solve the problem or not? Yeah, okay, that's easy. But if we can do algorithm selection, then we rely on these things called algorithm portfolios. And the name portfolio is inspired by economics. So this was actually proposed by people from economics in a paper. When was this? A long, long time ago, like 26 years ago now. And the idea here is similar to economics, to spread out the risk over multiple entities instead of relying just one. So if you want to invest in the stock market, then maybe you don't want to put everything into Bitcoin, but you also want to put some money on Dogecoin or whatever the cool coin is. Is there Tesla coin? If not, you heard it here first. So you want to spread it out so you minimize the risk of you going bankrupt because somebody does something that causes the price of Bitcoin to go down. Same thing here. We want to spread out the risk of essentially bad performance over multiple algorithms, so that we don't have we don't put all of our eggs in one basket. Different ways of constructing these in practice, but a popular way is to essentially have a look at competitions. So in constraint programming, this might be, for example, the mini-zinc competition, and then say, well, in the competition, these particular algorithms did well, so these are the ones that I'm going to put into my portfolio. If you're wondering about what else you could do, I don't really have any more slides on this because of time constraints, but I'm happy to talk about this in more detail later. Yes? Yes, so the paper does have a look at, if I remember correctly, 2 different types of computational problems. And the portfolio that they're using is really very simple, as in they simply run all the algorithms in parallel and then magically say, oh yeah, this is the best one. So not really something that you would want to do in practice, but they did show that they can achieve exactly this effect of minimizing the risk of bad performance by running more than one algorithm. But yes, so this is specifically for hard computational problems. I don't remember off the top of my head what these were. It wasn't SAT, which is kind of disappointing, but you know, yeah. But so they did apply this specifically in the computational context. Yeah, well, so yes. Now, I'm not entirely sure on the timeline. I think the phase transition stuff was just a couple of years after that, so around 2000, 2001, as in at that time this was still unknown, or, well, at least unpublished, right? Because people obviously intuitively knew about this beforehand. So at the time, it really, well, okay, it was published in Science, so I'm assuming that it made a contribution, but maybe I'm assuming too much here. But yeah, so this was right around this time when portfolios became popular in AI and people discovered phase transitions in various contexts, which I believe was right around 99, 2000, 2001, so just a couple of years after that. But I'm not 100% sure on the timeline. Any other questions before I move on here? Okay, so this is one of the first papers on all of this, and I've already mentioned this. So when I say algorithm here, I mean this in a very loose sense. So this can really be a whole bunch of different things. This could be, for example, a constraint solver. This could be a search strategy inside a constraint solver, or a modeling choice. So in particular, don't think of this as this is the thing that I run to solve the problem, but you're also making choices when you're modeling your problem, as we've already talked about yesterday, right? So, and in particular, then with things like CP/MPy, you can also choose to transform your problem in various ways, and depending on what type of problem you're solving, that might be beneficial or not. Also, then combining that with a particular solver. And it's really this entire space that I'm talking about here. So it's not just the actual software that you run. That's, of course, a main part of it, but there's a whole bunch of other things that goes into this as well. And then, yeah, so different types of consistency if we want to get into things like parameterized solvers as well. So think of algorithm here as a kind of catch-all in a very loose sense for anything that you're using to solve, for example, a constraint problem. Okay, a little bit of kind of terminology and background here, and I've sneaked that past you on one of the previous slides already, because when we have these portfolios and when we do algorithm selection, the question is always how do we evaluate this, and we usually have a look at 2 things as references. We have on one hand the single best algorithm, and this is simply the one that does best on average across the entire set of instances that we are interested in solving. And that's essentially what you would do if you didn't want to bother with all of this, right? You just choose the one, like the winner of the competition. That was clearly the one that did best on average. So I'm just going to go with that. I'm not going to worry about specifically for each instance choosing the best one because too difficult, or Tuesday morning and can't do it. And that gives us a reasonable lower bound on the performance of a portfolio. In particular, if we're not doing better than that, well, then there was really no point to doing any of this in the first place, right? We want to do better than that. And then on the other side, we have the virtual best algorithm, where we say that, well, we now have our portfolio, and we have a magic oracle that tells us for each problem instance, this is the best one. Don't question it, just use it. And if we have that, then we get an upper bound on our performance, because we cannot possibly do better than always making the perfect choice. So this is, of course, specific to algorithm portfolios, because if we're talking about things like automated parameter tuning, then I don't even necessarily know what the best possible performance is, and I can't necessarily bound it in this way. But for portfolios, these are two useful ways of giving us a feeling of what the performance looks like, because if we just have a number, like, we can now solve all problems in an average of 100 seconds, what does that mean? We need some reference here, right? And if we know that, well, for the single best solver, it was 150 seconds, oh, okay, we're now faster. We're quite a bit faster, right? So that looks good. If we then know that, oh, yeah, the virtual best solver is 99 seconds, so only very insignificantly faster, we know that we're really doing quite well in our algorithm section here. So two useful points of reference that, in particular, you will see often in the literature. Yeah, so and following up on what I said previously, the virtual best algorithm also corresponds to the overhead-free parallel portfolio. So I'm assuming that I can simply run everything in parallel and that there's no overhead associated with that. And then when the best thing finishes first, then I essentially forget that I ran everything and ignore the additional resources that I've put into this. Yeah, so and these are also called single best solver and virtual best solver in the literature, depending on what paper you're reading. So again, a little bit kind of terminology all over the place here, because this is applied in so many different contexts. Yes? I'm sorry, the virtual best in automated parameter tuning. So there we don't necessarily know that, because in many cases the parameter space that we're dealing with is infinite, essentially infinite. So as in, we cannot exhaustively evaluate this, and we'll have a look at that in a bit, because so this is kind of the other main difference between algorithm section and automated parameter tuning. For algorithm section, we assume that the number of different choices, the number of different algorithms we have, is small enough that we can essentially do an exhaustive evaluation, and then we build models that allow us to make choices based on that. But for automated parameter tuning, in particular, if our space is infinite, we simply cannot do this. And that means that we cannot even quantify the virtual best algorithm or the virtual best solver, because we don't know what it is. We cannot do this exhaustive evaluation, and therefore it is always entirely possible that there's something better out there that we simply haven't found yet. Does that make sense? Yep. So, and this is really, once we get to the automated parameter tuning part, the problem with this in general, in that we really don't have any guarantees unless we run everything for an infinite amount of time, which we usually don't have. We have no guarantee that we will reach any particular level of performance, that we will get within any particular epsilon of the best possible performance, which we also don't know. So this is really all inherently empirical. There's not really any useful theoretical guarantees in practice that can help you do this, unfortunately. Okay, so let me dwell a little bit on this point here of the overhead-free parallel portfolio, because you could ask, well, why don't we simply do this? In particular, if we have a relatively small number of choices, like, you take a bunch of the different constraint solvers and CPMPy, why don't I simply run all of those in parallel and forget about doing the stuff that I'm going to tell you about? It turns out that this is actually slower in practice, and in many cases, we simply have too many algorithms to run. So you might not have enough resources. Then this is also a massive waste of resources, because, well, you're running, a factor of 10 times more than you really need to. And it turns out that if you run this on an actual machine, which I'm assuming that you're going to do, then it tends to be slower in practice once we hit about 10-ish algorithms running in parallel. So here on this graph, MCP score, misclassification penalty, essentially, we want this to be as low as possible. So this is the penalty compared to the virtual best solver, essentially. And as you can see here, for a bunch of different algorithm section approaches and our single best solver here on the left-hand side for comparison, the total penalty increases the more things we run in parallel. So here for 1, 10, 20, 30, 32, etc., processors. And in particular, so really what we're comparing to is essentially this bar here or this bar here for performing algorithm selection. If I simply run stuff in parallel, what we have on the left-hand side, it takes longer. And that is simply because, well, as you all know, if I run more than one thing on a processor, everything tends to slow down because, well, we have only one cache, well, depending on which level of the hierarchy we're looking at, and everybody is accessing this shared memory through a shared bus, and that tends to slow things down in practice. So it really is worth it, unless we're talking about something like 2 or 3 algorithms, and then, yeah, okay, you can simply run everything in parallel. Okay, so hopefully I've convinced you that it's a good idea to build an algorithm selection system. So how do we actually do this? Well, most approaches rely on machine learning, and really all modern approaches, as in from the last 10, 20 years, rely on machine learning. Back in the day, as you saw, this problem was originally proposed in the 70s, and back then machine learning wasn't as hot as it is today. So back then people actually tried to come up with like handcrafted rules about, oh, in this particular context thou shalt do this, and here you should do that. But of course we don't do that anymore, because now we have machine learning to do that for us, and that can handle much larger amounts of data and make it much easier to apply in practice. So, and as we've already touched on, essentially the idea here is that I take my different choices, I take my different algorithms, whatever these represent, and I run these on some kind of training data. What that is depends on the particular context. That might be a set of constraint instances. That might be constraint instances from a particular family of constraint problems, if I'm interested in solving this particular family, or something broader if I'm interested in putting this into a competition and then hopefully winning the competition, as algorithm selection systems have done in various areas. And then I train on all of this data that I get. And we'll get a little bit into the different types of models that I might be training. And as usual in machine learning, you've had the introduction to that yesterday, I then want to evaluate the performance on a separate set of test instances that the system hasn't seen during training. And you can see the problem with this, because this will involve potentially a large amount of prep work. If you want to do this for a large and broad and varied set of instances, so you really want to have a system that gives you good performance in general and really knows, oh, this particular type of problem that I'm solving here, I need this solver, etc., then you might be literally spending CPU years just getting the training data for the system that you want to run. We'll get, when we talk about automated parameter tuning, we'll have a look at doing this a little bit cheaper. So yes, how do you choose your instances? Because in the end, just like any machine learning system, we want what we learn to generalize. So we want an algorithm selector that doesn't work well just on one particular small set of instances, but ideally on at least a family of constraint problems, and probably on something, again, that will win you the competition. And in particular, in this context, we need to balance the easy and hard instances. There are some approaches that try to learn on easy instances and then apply this on hard instances, as in there's less overhead for the training data, because I only choose the problems that I can, for example, solve within a second or so. But that tends to work well in some cases and not so well in other cases, because the easy problems are not necessarily representative of the hard problems that we eventually want to solve in practice. And yeah, so we may need hundreds or even thousands of instances, so there's a large amount of experimental overhead involved in setting all of this up. Okay, so once we have all of that, here are the key components of an algorithm selection system. It is really relatively simple. We need something to extract information from the instances we want to solve. So this is what we feed into our machine learning system, and that allows us to then make the decision on this particular problem you want to use solver A, and on this other problem here you want to use solver B. And we need some kind of performance model. So this is what we train with our large amount of prep work and with the training data that we've extracted by running all the different algorithms on all the different instances. And then we need some kind of prediction-based selector or scheduler. In the simplest case, this is simply saying, well, this algorithm here has been predicted to have the best performance on this particular instance, so that's what I'm going to go with. But we can also get arbitrarily complex here, where we can say that, well, you know, here's the top 10 algorithms, and I'm going to schedule these in some way, and I'm going to schedule these on not just one machine, but multiple machines, and I'm going to take into account the overhead that this introduces, etc., etc. So we can really get quite sophisticated here. Optional, but in practice important, are things like a pre-solver, because the first step here, so the feature extraction from the instances that we want to solve, introduces a certain amount of overhead. So before I can even make the decision which solver to use and start running it, I need to get some additional information. And if I simply run, for example, the single best solver, I don't need to do this, so I already have a head start. And this is the idea of the pre-solver, to essentially take something that is a reasonable default, for example, the single best solver, competition winner, something like this, and run it for a relatively short amount of time to essentially see whether the problem that we want to solve is really easy. Because if it's really easy, then we can solve it in, say, a fraction of a second. And if it would take 2 seconds to extract the features that we need to run all of this machinery to eventually choose the best algorithm, then we have lost no matter what we do, right? We could choose the perfect algorithm, but we're still going to be slower because of that. So that's the idea of the pre-solver. And then you can also really get arbitrarily sophisticated with your performance models there, because you could have, for example, models that predict how long is it going to take to extract the features. Because in some cases, that might take actually longer than solving the problem. And if my prediction says, yeah, OK, on this problem here, it's going to take 3 days to extract features, then maybe I don't want to do this and simply go with the single best solver. So we can, again, make this almost arbitrarily complex. But here, we're going to keep it relatively simple. OK, so let's, first of all, everybody clear about the general setup here. We're going to dive into the individual bits and pieces a little bit more now. So I want to make sure that everybody is clear on how all of this fits together. Yes, good, excellent. OK, features. The idea here is that we have some information, we get some information from the problem instances that we want to solve and relate that to the performance that we eventually observe given particular solvers. And we also want these to be relatively cheap to compute. Because if they are expensive to compute, in particular if they are more expensive to compute than solving the problem, really there's no point to it, right? I mean, obviously the ideal feature would be I take all the algorithms that I'm interested in and I run these on the particular problem, and I take the runtime, if I want to optimize runtime, as the feature value. And that gives me the perfect information, because then my selection becomes really, really easy. But I also don't have, you can't hear me anymore? No? How about now? Now it's good? OK. OK, where was I? Yes, relatively cheap to compute, because if they are too expensive to compute, then none of this is worth it anymore. And that we obviously want to avoid. Usually these are specified by a domain expert, so this is kind of a little bit where this whole black box thing breaks down, because we do need somebody who knows something about constraint problems, for example, to then say that, oh, OK, here's a property of a constraint problem that I can compute relatively cheaply, and that tells me something with respect to the expected performance of a solver or a set of solvers on this. Then we can classify these into 3 different categories here. So the simplest features are the syntactic features that I can extract by simply looking at the description of the instance. So this might be for that my CNF formula, or for the constraint problem, this might be the Python CPM Pi code, or whatever system we're using. So I simply have a look at this, and then I do things like, for example, count the number of constraints. Then we have the probing features. These tend to be more informative, but also more expensive, where I take an algorithm, and this doesn't need to be a real algorithm. This could be some kind of pre-processing and run this for a short amount of time. So for example, I could do things like unit propagation, 1 step of unit propagation for SAT, and then see how that changes the problem. So how does that make the problem more, well, easier, and how does that give me some idea on where the solution might be, or whether there is a solution or not in this case. And that should then also be indicative of the performance that we see when we actually run the algorithms that we want to solve them. And the third class of features that I'm going to talk about here are dynamic features, where we essentially keep track of what's happening while we're solving the problem. This could be, for example, that we've started to solve our constraint problem, and we started branching, and we have a look at the search tree, and we observe, based on the propagation that happens inside the constraints, how we reduce the size of the search space as we go on. And these types of features are less useful for selecting, before I start solving a problem, what kind of algorithm I want to use, but they are useful if I want to monitor what's going on while I'm doing this. So for example, for things like, was that actually a good choice? Or do I want to switch the algorithm because the problem has some unexpected properties that only became apparent once I started solving it, as in it was much easier or much more difficult than I had anticipated by just looking at the problem description. Things like this can help us do that. Okay, so here are some examples of syntactic features. I've already mentioned number of constraints. Similarly, we can have a look at the number of variables. And of course, we know that the ratio of these two is related to the phase transition, which we briefly talked about earlier. So we have there is some good evidence to suspect that the clause to variable ratio, for example, is informative with respect to the hardness of the problem and with respect to how long it will take a particular solver to solve this particular problem. Then we can have a look at things like the order of variables and the values in the domains. We can have a look at various graph representations of the problem. So for example, for constraint problems, we can have a look at the primal graph, where each variable is a node, and the nodes are connected by edges if they're in the scope of the same constraint. And of course, once we have a graph, we can do all kinds of analyses on graphs. So we can, in particular, have a look at node degrees, the connectivity of the graph. We can have a look at clustering coefficients, small world properties, etc., etc. And again, there's good reason in the constraints context to believe that this gives us some useful information. If you think, for example, of the tree width of the primal graph, which is related to the difficulty, to the hardness of the problem. All of these are really relatively easy to extract, because you just have a look at your problem representation and you count, for example, the number of variables and the number of constraints. Once you get to graphs, a little bit more difficult, because there you need to obviously build an additional data structure, but even that is still relatively straightforward. And there's lots and lots and lots of these. So I'm happy to, if you're interested, point you to papers where you can have a look at, I think, hundreds and hundreds of different types of features that you could extract from your constraint problems. Probing features. I could, for example, say that, well, I'm going to take this algorithm here and I'm going to run this for a small amount of time for suitable definitions of small amount of time. Let's say less than a second for the sake of simplicity. And then I'm going to have a look at the number of nodes in the search tree that I explored during that time, or the number of propagations that happened, or the domain reductions that happened, or some kind of estimate of the search space size based on what happened during that small amount of time. I can also do things like estimate the tightness of a problem or individual constraints by essentially sampling from the domains of the involved variables. For all of these, I have to actually run things, so this is a little bit more difficult. And it also tends to take more time, because in particular for the estimate of the search space size, obviously the longer I run this, the better my estimate becomes. So I have to balance this trade-off of how long do I want to run this versus how good is the information that I want to extract from this. Because obviously, again, in the limit, if I run this for the entire time it takes to solve it, I have the perfect estimate of the search space size. It's not even an estimate anymore. It's now the ground truth of the search space size. So really, really useful in making the decision which solver to use. But I've already also solved the problem. So really, I don't need to make that decision anymore. And in particular, I haven't gotten the benefit of choosing the best solver. So I have to balance all of these in practice. Dynamic features, changes to variable domains. So as we go on searching through our tree, how do we reduce the domains of individual variables, number of times a particular constraint propagates, and then we can also have a look at what that actually does. So did that actually remove values from the domains of the involved variables, or did I just run a whole lot of stuff and not see any reductions in domain size? The number of failures a clause participated in, if we're talking about SAT solvers, and all kinds of other stuff that I can monitor while we're solving the problem. Now, these features tend to be really quite expensive, both in terms of what I need to do to actually get them, because for this I need to instrument the constraint solver. I can't simply treat this as a black box anymore. I now need to go in, and if you wanted to do this with CPMPy, for example, you would actually have to look at the source code and potentially modify it and say that, oh yeah, okay, here some kind of propagation is happening, so let me introduce a global variable to keep track of this, or something along those lines. But then also running this, once we've implemented this, or if you find a solver that already supports this, because I need to maintain all of this information while I'm searching. And in particular, I need to do this, depending on how I set it up, at every node of the search tree. So this is something that happens really, really often. And in particular, it might be very expensive compared to the actual search that happens. So for example, if I'm at a search node, and I can't do any propagations, I can't remove any values from domains, then that might be relatively cheap. But if I need to keep track of this, the overall amount of work I need to do at that node is still quite a lot. And this is, if you're not very careful with this, a really good way of building a really, really slow constraint solver. So I wouldn't recommend this, because this is really quite tricky to do in practice, and also really goes away from this black box paradigm that I mentioned at the beginning, where we now need to know what actually happens inside the solver, and then also we need to be able to modify it in suitable ways. Okay, so obviously the ideal thing to do is no features, where we simply throw deep learning at it. And there's a bunch of approaches that have gone in that direction. Obviously, the benefit of this is that I can now again go back to treating my problems as a black box. I don't need to have an understanding of, oh, there are constraints and there are variables and they have these relations, and the clause to variable ratio or the constraints to variable ratio is something that is meaningful with respect to the hardness of the problem. I just give it all to a suitable deep neural network and then hope that something comes out. So the first work in that direction was, when was that? About 7 years ago now, published at AAAI, and that didn't really work all that well, but it was also a relatively simple approach. And then more recent work that some of the people in this room were involved in on using graph convolutional neural networks to solve MIP instances better. Again, not really going into more detail on that, but if you're interested, I'm happy to give you more pointers, and in particular, point you to the people in this room that were involved in some of the later work on that, who would be able to tell you more. Okay, right, what features of these do we actually need in practice? Because I've talked about lots and lots of stuff that we can extract in different categories, but as with most machine learning problems, in practice, we don't really need all of these. And of course, we also want to keep, in principle, the number of features as low as possible, because extracting these involves a certain overhead. The more features we have, the more complex our models become. So that means that it takes longer to train those. We need more data that we need to move around potentially, and we also have a higher potential for overfitting with more complex models. Now, the good news is that in practice, we often only need a very small number of features, and this is one of the things we found out in ASLib, in the algorithm section benchmark library that Tias mentioned earlier, where we did do the feature selection for a bunch of different scenarios for algorithm section, so essentially different problem domains, and found that in many cases we can really reduce this from more than 100 or a couple of dozen to 3 or 4. So usually it's really only a small fraction of all the features that we could extract that contain enough information to help us make this decision which algorithm to use. And yeah, so in the end, really just use whatever works best. So I'm not telling you that, oh, you should absolutely use this type of feature, or this feature is always very important, because it really depends on the particular context. Yes? That's a good question. I don't remember off the top of my head. So certainly what we saw when we did the feature selection for ASLib was that it was not really consistent. So as in depending on the particular setup and the particular set of algorithms and the particular set of problems, you end up with different features that are important. I am not sure if that also, I don't think we did it specifically for the algorithms because that also gets into, well, what kind of performance model are we going to use, and we'll get a little bit into that. But I would expect the same thing there, so that depending on what algorithm you're using, different types of features tend to be more or less important. In particular, if we talk about these probing features, because in some cases, they literally quantify what the algorithm does because the algorithm involves a preprocessing step, or it might be the actual algorithm that we're running for a short amount of time. And in other cases, it might be not related at all because the algorithm is simply set up in a very different way. Any more questions before we get to how we can do this modeling? How are we doing for time? Okay, I should probably speed up a little bit here. Okay, simplest way of doing this, we do a model for the entire portfolio. And we treat this as a classification problem where we say that the label that we want to predict is the name of the algorithm. And there are variants of this where we can combine this with unsupervised learning. So we cluster, and then we essentially identify the best algorithm in each cluster. And yeah, different variants of this. In particular, if you're treating your algorithm selection problem like this, then you do want to attach some kind of weight to each instance, because remember the graph that I showed you way back at the beginning? For some of the crosses there was really very little difference between the approaches, and for other crosses, for other instances, there was a massive difference. So we want to put emphasis on the problems where there is a massive difference, because these are ones we care about, these are ones we want to get right. We care less about the ones where, you know, making the right or wrong choice has a difference of 1%. Yeah, okay, if you make the wrong choice there, I'm not really that bothered. But if it's an order of magnitude, then yeah, I do want you to get this right. So that's why we can use various techniques to, when we're training these systems, make sure that we're putting more weight on these instances. Another popular approach, we model individual algorithms. So this is kind of the direction in which the question was going in just before, where we take each algorithm separately and we build what is sometimes called an empirical hardness model in the literature. So essentially, given this type of problem here, as characterized by the features that we have extracted, how long do you think it would take to solve this particular algorithm, this particular problem with this particular algorithm? And we can obviously do this for all kinds of other performances. So for example, if I'm interested in accuracy in the machine learning context, or if I'm interested in memory consumption, works exactly the same way. And then we, of course, need an additional step after we make predictions, where we take all of these predictions and we combine them to take the best one. And what that means depends on the particular context. So obviously, if I'm interested in optimizing runtime, then I want to choose the one with the lowest predicted runtime. If I'm interested in optimizing accuracy, then I want to take the highest accuracy, and so on and so forth. Yeah, and this is the approach that was used in Zilla, one of the most popular, one of the most successful algorithm selection systems that we'll have a little bit of a closer look at in a bit. But let me finish the types of models first here. So then we can also, again, we can get arbitrarily complex with this. So we can build hybrid models where we kind of have something that considers the algorithms individually, but also then together, for example, pairs of algorithms. So instead of predicting performance of an individual algorithm, we're predicting performance differences between two algorithms. And the intuition here is that this is often easier. And in particular, also what we're really interested in, the actual performance of an algorithm doesn't matter that much. What really matters is the relative performance compared to the rest of the portfolio. So here we're making that explicit. But of course, then we also, unfortunately, need to maintain and run and train more models here. But this is an approach that tends to do quite well in practice. Overview of a bunch of the different things that I've talked about here. So if we model the entire portfolio at the top here, then we essentially want to make a classification which algorithm to use in which case. For individual regression models, we predict the performance, and then we choose the best one based on that. So here I am maximizing, so that is, I don't know, some kind of measure of the quality of the solution that's achieved, for example. I can do this in a pairwise fashion for both the classification and regression approaches. So which one of these two algorithms is going to be best? I do that for all pairs, or what is the performance difference between those two algorithms? And again, I can do that for all pairs. And that then, as I said, makes the selection afterwards a little bit more difficult. But of course, I also have more information available that I might then be able to use, for example, to schedule my algorithms better, where I not only know that this is the best one, but I also know that, well, these are the ones that come after it, and I can quantify the performance difference between them. And then I might want to, for example, allocate resources according to the predicted performances or according to the predicted performance differences. Yes, okay, so once we have these performance models, what can we do with them? That depends on the type of performance models. We can always get the best algorithm because that's kind of what we set out to do in the first place. So if we can't do that, then really our performance models are not suitable. If we have something that doesn't consider only the entire portfolio at once, then we can also get the n best algorithms ranked. And we can, again, use that, for example, to allocate resources to our n best algorithms. And if we're using dynamic features, we can also answer questions of, should I change the currently running algorithm? Because it turns out that the problem is, for example, much more difficult than I thought, and that means that I might want to switch to a higher level of consistency if I'm solving my constraint problem, and various things along those lines. So bunch of references here that take different approaches to that, and of course there's a lot more in the literature. So if you're interested, happy to point you to more references, and this is just my opinionated selection on some of the more representative approaches here. Okay, almost at the end here. Then the only other thing that we need to decide is, when do we make a prediction? If we only choose once before we start solving the problem which algorithm we're going to use, that's easy, right? Well, that's exactly when I make the prediction. But of course, I have no recourse if my prediction is bad. So I chose the wrong solver. Well, I'm stuck with it. Nothing I can do. I can also make these predictions continuously. So for example, using these dynamic features. And that does mean that I can now react if I see that something has gone wrong. So either the problem is very different to what I expected, or the solver is not performing as well as I expected for whatever reason. I can now address this, and I can change the algorithm. But of course, that requires me to continuously make these predictions and to continuously measure the dynamic features, for example, which introduces overhead. So that means that even though I might be able to make a better prediction and better decisions, it's still not worth it in the end, because I have to run all of this machinery all the time. So that there's a trade-off there. And again, how exactly you want to do this really depends on the particular context. So there's no kind of, oh, this will always work or this will never work. It really depends on what specifically you want to do. Okay, let me wrap up the algorithm section part here by having a look at two example systems in a little bit more depth. So Zatzilla, I mentioned already, was probably the first successful algorithm section system. As the name suggests, this was for SAT, not for CP, but hey, I mean, they're close enough. So there's many different versions of this, and I chose one of the earlier ones here, but depending on what paper you have a look at, those numbers might not match exactly, so just be aware of that. But we're roughly looking at a portfolio of a relatively small number of SAT solvers, so in one instantiation this was only 7, and this was composed of competition winners, as I said before, a popular way of doing this in practice, and trained on a relatively large number of instances, so a couple of thousand here. Just again, to give you a rough idea of what the numbers involved are. So we're not looking at, you know, millions and millions of instances, as we might for deep learning, but we're also not working with 5, so it does have to be a substantial number. And it used here relatively small number of features, mostly syntactic, that we can extract by just looking at the problem instance, and a couple of probing features here. Yeah, okay, so and then we predict the runtime, or rather the log of the runtime for each individual solver of the 7 in the portfolio and choose the one with the best predicted performance. The type of model that was used changed throughout the lifetime of Zilla, so this evolved over many years, and not only the type of machine learning model, but also the type of algorithm section model and performance model changed over time here. And it included all the bells and whistles that I talked about before, so things like I want to predict how long feature extraction is going to take, and I want to run the pre-solver to, in particular in a competition setting, not die because I take so long solving the easy instances, because as it turns out, a lot of the instances used in the SAT competition are really quite easy, as in they can be solved in a fraction of a second by almost any SAT solver, and certainly by the one that you would choose as the sensible default, so the winner of last year's competition, for example. Yes, so and this won the SAT competition several times, which made the people that develop SAT solvers quite sad, because this didn't develop a SAT solver. So at some point, they had changed the rules of a competition to say that you can't run systems like this anymore. It does have to be an actual SAT solver. And now there's a separate track in the competition for these types of systems, so that you can still enter them and you can still win something, but you're not directly competing with the solvers and with the people that have put a lot of work into making these solvers better, and then you're just taking the solvers and doing this weird machine learning thing on top of it, and you're beating them. Clearly, we can't have that. Here's a more recent system. As somewhat sparse description here, because this is using graph neural networks to solve mixed integer programming problems better by choosing variables to branch on. Again, if you're interested, we can talk about this in a little bit more detail, but here's really just a rough overview. In particular, kind of the evolution from one of the earliest systems that was really quite complex and that a lot of engineering went into over many, many years, starting with what features do we want to extract over. We have tons of different types of models that give us all kinds of predictions, to something relatively simple, if you can call graph neural networks relatively simple. Well, for suitable definitions of relative, that is much, much more recent. Okay, as an aside, one recent development, we can now also characterize the solvers that we're using automatically extracted features. So we can analyze the source code, and we can also analyze binaries to inspect information similar to how we do this for problem instances, and then use this for better algorithm section systems as well. Again, happy to give you more detail if you're interested in this. Just come in and talk to me about that. ASLib, TS has already mentioned this. So if you're interested in this, then you can find a whole bunch of information on different scenarios and different approaches and code to build algorithm section models and to do comparisons and automated parameter tuning, which we'll get to in a second, and all that kind of stuff at this website here. And all the data is available on GitHub, so you can, you can download this, you can work with this. There are no restrictions on this. And they represent a bunch of different domains in for combinatorial problem solving that algorithm section is usually applied on. Okay. Now let me get back to automated parameter tuning. Okay, how am I doing for time? Not that great. Okay, well, we will do this in some way by speeding up. So here's the problem again to remind you. So now, instead of having a relatively small set of distinct things, we have a potentially infinite set of different configurations, and we want to find at least a good one, a reasonable one, something that's hopefully better than what we started with on a given set of problem instances. And again, similar to algorithms, when I say parameters here, I mean this in a very, very broad sense. So really anything that you can change that makes sense to change and that hopefully also impacts performance. Could be, for example, search heuristic, variable ordering, global constraint decomposition, etc., etc. You do have to be a little bit careful with this, because there are usually all kinds of parameters that you do not want to change, such as debugging output. That might affect performance in that it will make things slower, but if your automated parameter tuner discovers that you want to turn off debugging output, well, okay, we kind of knew that beforehand, right? Then you also want to be careful with this if you can set, for example, a random seed, because you do not want to tune this. So this would be kind of the poster child for over-tuning, where you tune your random seed to do really, really well on a particular set of instances, and this will obviously not generalize to really anything else, so don't do that, and be careful when you set up your tuning problem. Yeah, here's some examples. So spare stat solver, for which I showed you some results way at the beginning, has 26 parameters, so relatively small. If we get to MIP solvers, Cplex has 76 parameters. This is a couple of years old now, so the number might have changed. And then if we talk about machine learning, for example, the Weka package, which TS has already mentioned at the beginning, then we are talking about a much, much larger space. So as I said, potentially these spaces can be infinite. In principle, this is what we want to do here. So we have some kind of configurator, and the only thing that we have to specify as the user is really the parameter values and what these different parameters are, how these can be set, and ideally also dependencies between them, as in if you set this parameter, this other parameter has to be this particular value, these kinds of things. Then I have my target algorithm that I want to run on a particular set of problem instances, and that might be one problem instance if that's a particular difficult one that I'm interested in solving very efficiently. So I call it multiple times with different parameter settings. I get the solution cost back, so some kind of measure of performance. This could be, for example, the time it took to solve the problem, which goes into my configurator, and based on that, I make the decision on what parameter configuration to evaluate next. Very briefly, what do these parameter spaces look like? We can have numeric parameters, so like 1, 2, 3, where we have some kind of ordering, and we also have an idea of what the difference between the different values is. 2 is obviously twice as much as 1. Whereas 3 is not quite twice as much as 2, so I have some idea on what these values, different values might mean. Ordinal, I have some kind of ordering, but I don't really know what the difference is. Is the difference between A and B bigger than the difference between A and C? Well, can't really tell. Categorical, yeah, just strings. I don't even really have an ordering there. And I've already mentioned conditional dependencies that I might have there. Depending on what type of parameter space you have, tools might not be suitable, but there are also ways of converting parameter spaces into one another. Here's a general approach. We want to evaluate our algorithm as a black box function, just as before, where we said we have these different algorithms that we want to choose from, and we don't really know what they do internally. So we want to essentially observe the effect of tweaking the parameters without knowing what's going on inside, because we don't want to become experts in the particular solver that we're using, which might take a couple of years. We really just want to solve the problem that we want to solve right now more efficiently. Based on that, as I said, we decide where to evaluate next. In particular, we have to balance diversification or exploration and intensification or exploitation. So essentially, to what extent do I want to focus on parts of the parameter space where I have observed good performance versus going to other parts of the parameter space where I know nothing. So there might be something good there, but maybe there isn't. So we have to trade off these different things. Yes, the other problem is knowing when to stop. So most algorithms that we deploy in practice are anytime algorithms, as in we can really stop these at any point. But how do we know that now is a sensible time to stop? And the short answer is, unfortunately, we don't, because most approaches are incomplete. If the space that I'm exploring is infinite, then obviously I will never have the complete picture of performance, right? I will never know that this is the absolute best I can do, and I cannot possibly do any better except in special cases. So no guarantees of optimality, not guaranteed to find an optimal solution, or maybe the optimal solution is the first thing that I find, but I will not be able to prove that it is the optimal solution. And it will my configurator make look bad because it looks like I'm not improving. Yes, so how do we stop in practice? Well, usually it's some kind of a time budget, right? Because, well, you're working on the paper and there's a deadline. There's only so much time you can spend on optimizing this. You have to stop at some point, and then you go with whatever you have then. Of course, this is not entirely trivial either, because if I run something for too long, then I waste resources. If I run it for too little time, then I have a suboptimal result. One way of approaching this is to use statistical tests. In particular, if you compare something to the default configuration, as in is this statistically significantly different to what I started with. If so, and I know that it's better, then I might say, yeah, okay, I'm happy with that, and that's what I'm going to go with. We can do various things to speed this up in practice. For example, evaluate only on parts of the instance set, or use a technique called adaptive capping, where I essentially, if I'm optimizing for runtime, change the time limit dynamically. If the best configuration I found can solve this problem in 10 seconds, there's clearly no point in letting something run for more than 10 seconds. If I then find something that can solve it in 5 seconds, there's no point in letting it run for more than 5 seconds. So I can adjust this dynamically and speed up through that in practice as well. Okay, here are very simple approaches, 2 very simple approaches for doing this in practice. I can do a grid search, shown on the left-hand side here, where I simply take my parameter space and I take some kind of discretization of this. So if the space is infinite, then obviously I have to be very careful with that discretization because, well, I can't run an infinite number of experiments in practice. Or I can do, on the right-hand side here, a completely random layout where I simply randomly sample from my parameter space. The great advantage of that is that this is really, really easy to implement. So you can do that in half a line of Python, essentially. And it tends to work really, really well in practice as well. OK, a little bit more intelligent. We can do local search. And there's many, many variants of this out there. But the idea is, in principle, that we start with a set of random configurations. So we take some random samples from our space. These are our initial configurations. And then we do a local search step. So we make a small change, whatever small change means in that particular context, to the best configuration that we've found so far, the best point we've evaluated. We check that. If it's better, then we keep it. Else, we go back. You've probably all done this, right? If you do hyperparameter tuning or parameter tuning manually, that's essentially what you do. You find something that works well, and then you try to tweak it in small ways. And if that works, hey, great, and let me try something more in that direction. Else, go back and try something else. You can also optionally do random restarts. So at some point, you've tweaked it, and you've tried this way, and you've tried that way, and you haven't really found anything better. So what do? Well, you do something random, and you start again somewhere else. This is what this looks like in practice. So here, we, without loss of generality, want to maximize. So we essentially want to find this peak in the middle here. We do some random initialization, evaluate our point. We do a local search step. So we identified a way in which to improve our configuration here by making a small tweak and observing better performance. And we can continue doing that until we find our local optimum here. At that point, we're going to be stuck with local search, because none of the small changes we can make will get us away from this, because they will always show us something that is worse than the peak we found so far. So we do a random perturbation or a random restart in a different part of the space, and here we get lucky, and we're now on the slope that will eventually lead us to the global optimum here. So we have identified that here now. And then, of course, we have to decide between those two. So we select from amongst the local optima that we found so far. In this case, very straightforward, because clearly the point I found second, the optima I found second, is much, much better than the one I found before. OK, so that's also relatively easy to implement. You just have to decide what your local search step is, and then off you go. And one prominent example of local search algorithms are genetic algorithms, where exactly this happens, except a slightly fancier version. So you do lots of this in parallel to better use your resources. We can also do this more intelligently by using model-based optimization. This setup here is essentially the same, except that instead of more or less blindly searching through the space with our local search steps, we have what's called a surrogate model that gives us some estimate of the performance in particular parts of the parameter space. And this more or less exactly corresponds to what you would do as a human, because if you're doing this manually, you're of course not doing this completely randomly, right? You have a mental model of how the parameters and their values affect the performance that you see, and based on this mental model, you decide where to evaluate next. And you revise your mental model as you observe more and more data. So if you think that something is good, and then you see that it's actually bad, you're not going to continue believe that you will see good performance there. You revise your beliefs, and that's exactly what's happening here. So again, we start with a relatively small number of initial configurations that are, for example, randomly sampled. We use machine learning to induce our initial surrogate model, and then we use that model to predict where to evaluate next. So essentially, instead of trying to figure out where the good performance configurations are on the underlying process that is expensive to evaluate, we do that on our surrogate model, which is cheap to evaluate. So we just make a prediction which might take a small fraction of a second. And then we simply repeat this process. And more so than local search, this allows a very targeted exploration of the promising configurations. Yeah, so this is roughly what this process looks like. In the literature, this is also often called Bayesian optimization. So again, different names depending on what paper you're looking at. Let's have a look at what this looks like in practice. So here in the top panel, we have the underlying function that we want to optimize. So this is the solid line, the kind of quadratic thing overlaid with a sign here. This is what is not known in general. So here, for the sake of being able to show you what's happening, this is shown. But in general, we do not know this. And then we have the estimate of this, of our surrogate model. This is the dashed line. And as you can see, this is really quite a terrible approximation. In particular, the optimal point here, the minimum that we want to find, we're not estimating that good at all. The model actually thinks that there's going to be something that's bad there. Based on the performance that we observed so far, so these are the red circles here and the green point there. This is the data that we have used to fit this particular surrogate model in this particular iteration of the optimization. And the gray shaded area here shows you the uncertainty of the predictions of our surrogate model. In particular, it's 0, where we know the ground truth. No uncertainty there. We know exactly what the value is going to be. And then the further we get away from these points, the larger the uncertainty of our prediction becomes. In the bottom panel here, we have what's called the acquisition function. This essentially takes the predictions of the surrogate model and mangles that together in some pseudo fashion to tell us where we should evaluate next. So the next proposed point to evaluate, the blue triangle here, coincides with the highest peak of our acquisition function, which is here expected improvement. So we expect to see the largest improvement over the best point we have found so far at this point here. So this is the point where we're going to evaluate next. We make that evaluation. We found that, well, actually our prediction was really quite accurate. We update our surrogate model, so we fit it again to the augmented data. So now we have one more data point. And then you can see that the next proposed point is now on the other side of our optimal point that we found so far, this red circle here. So kind of intuitively, again, we're doing something very similar to what you would do as a human, right? You find the best point. You go to one side. Oh, hang on, that was worse. Let me try the other side. Well, hang on, okay, that was also worse, so we didn't see an improvement there. Now something slightly more interesting happens, where the acquisition function essentially tells us that we want to go into an area of the parameter space where we don't have a lot of information. So now we are starting to explore. We're not exploiting and remaining in a part where we have observed good performance, but we have now satisfied ourselves that here, in this area, there's not really going to be anything better. We have found a good point. We've looked to the left and right of it. That was worse, so we don't expect to find something better there. So instead, we're going to a part of the parameter space where we don't expect to see good performance, the dashed line here, but our uncertainty, the gray shaded area, is relatively large, so there could be something good. And of course, here we get lucky because our predictions and our surrogate model was pretty bad there. So now we revise this in our next iteration. And then exactly the same happens again, where we now look, again, in the neighborhood of the best point we found so far. And we keep doing that a couple of times until eventually, okay, one more, until eventually we have again satisfied ourselves that in that particular part of the parameter space, we're not going to find anything better. We've now done a bunch of evaluations. We've identified a good point there. So our next evaluation would be here at the edge of the graph, where, again, we don't think we will find anything good. So the prediction is not good, but also our uncertainty is large. Now, of course, if we were to do this, then we would immediately move away from this, because here it turns out that we're actually much, much worse than the surrogate model estimated. Okay, so Yeah, in practice, this is unfortunately not quite as easy as I just showed you, where we have this one-dimensional and really quite nicely behaved parameter space. Very often, we have poorly specified parameter spaces, and this is not necessarily in terms of it doesn't represent the actual parameter space, but with respect to things like there are parameter configurations that will give us incorrect results, and there are parameter configurations that will make the algorithm crash. And then we have to handle those, because if we don't, and if we optimize for runtime, then we have essentially something that finds a parameter configuration that crashes really, really quickly, because, yeah, that runs really quickly, crashes immediately, but not quite what we had in mind when we set this up. So we do have to be careful there in practice. Again, don't configure on random seeds, because that will lead to over-tuning, and you will get something that will work really well on the particular set of instances that you evaluated on, but on nothing else. And we also, again, just like with algorithm selection, have to be careful with the instances that we configure on, because we want this to generalize, right? We want to find a parameter configuration that is not only good on the particular set of instances that we ran the configuration on, but then hopefully also on something else, and something more difficult or more general, or new instances that are not available when we do the configuration. Right, yes, so beware of overtuning. Conceptually similar to overfitting in machine learning. We end up finding something that works really well in this particular context, but for nothing else. So as in, it is really more or less completely useless in practice. And there are many ways that this can manifest itself. That said, we can actually also leverage this to essentially have tune a set of highly specialized algorithms that we then put in a portfolio together. So we can combine the two things that we talked about to get better portfolios by specifically tuning algorithms that give us good performance on small parts of the instance space. But because we're putting this in a portfolio, we can still leverage good performance overall. Right, so let me summarize here and finish almost on time. And so we have algorithm selection, where we want to choose the best algorithm for solving a problem, and then algorithm configuration or automated parameter tuning. Again, depending on what literature you look at, there might be different terminology for the same underlying thing, but we want to choose, in this context, we want to choose the best parameter configuration for solving a particular problem or a particular set of problems with a given parameterized algorithm. Both of these are mature research areas, so I've shown you some of the earliest papers which go back many, many decades, and effective tools are available. So if you're thinking of doing this, don't code this from scratch, but use a tool that already exists. That said, for the exercise in a bit, you will be coding this from scratch, or rather, you will be using the code that where I coded this from scratch, just to get a better understanding of what happens underneath the hood. But when you want to do this in practice, just use an off-the-shelf tool, and there are lots of different things available. And a shameless plug for the COSIA group, Configuration and Selection of Algorithms. So we've had annual meetings, more or less, with pandemic-induced breaks since 2012. This was the last one, so earlier this year in Paris. As you can see, it's quite a large group. The next meeting will be next year in Dresden. Dates haven't been fixed yet, but probably around May-ish. So if you're interested in the area, feel free to come by. These are usually very informal meetings, not a lot of talks, but poster sessions and lots of chances to talk to other researchers about what you're doing in this space or how you might be applying these techniques for your particular research. Here are some resources which I'm going to skip in the interest of time, and you've got the slides so you can have a look at this. Again, an opinionated selection of a very large body of literature and tools. If you're interested, come and talk to me. And with that, I'd be happy to take any questions in the last 2.5 minutes that we have left in this session. So, any questions? Where was this picture taken? Thank you. Great question. This is about a 45-minute drive away from both my home and my office in the Rocky Mountains. In this case, I got up quite early to catch a sunrise there, but highly recommend it if you're in the area because extremely scenic. Any other questions?
In your opinion, what are the next research challenges
Yes, that's a very good question. So this is a very broad field, and at the moment, more momentum for this in general is actually in the automated machine learning space, and not so much in the automated parameter tuning space for things like constraint solvers and combinatorial solvers, because that we can already do quite well. But for example, things like neural architecture search tend to be extremely challenging, because there each individual evaluation is really, really expensive, as in, you need a week on a couple of GPUs that will set you back like 100,000 euros or something like that. One of the areas that is starting to gain some traction in that space is multi-fidelity optimization. I've kind of touched on that already a little bit. The idea here is that while we're configuring, instead of doing full evaluations, we do a kind of partial evaluations. So in the context of neural architecture search, that might mean that I don't train my neural network for 50 epochs or whatever it is, but only for 10, and that will give me some idea of what the performance is going to be. So similar idea to the probing features that I've talked about, and then we use that information to do the configuration rather than doing the full evaluation. So really, I mean, if I kind of, one thing that is kind of spanning across all of these is how can we do this better in practice, and how can we get more information from shorter and cheaper evaluations. That's one of the main challenges. Also in this space, because, as I said, potentially a large amount of prep work, right? Not ideal if you just want to use this. So how can we do this better in practice without having to manually specify features and run all kinds of expensive overhead before we can get even started on this? Any more questions? No? Yes? Yeah, that's also to some extent an unsolved problem. I say to some extent because you can solve this by simply running multiple times and then averaging the result in some suitable fashion. Of course, this also means that all your experiments become a factor of, 10 more expensive, which usually is not really feasible because, well, you're already running on the cluster for a week, so you can't run on the cluster for 10 weeks. This is unfortunately really an unsolved problem, because in some cases, and this even depends on the particular algorithm and the particular machine that you run on the particular instances, we can see very large differences just running exactly the same thing multiple times. And this then obviously comes with all kinds of problems. So there was a paper a couple of years ago that essentially showed that for the SAT competition, you could get any arbitrary ranking of the top 3, as in the actual winner could be third, and the third one could be the winner, and the other way around, and the second could be the winner, etc., by just running exactly the same competition multiple times for exactly this reason. So there's, unfortunately, large amounts of noise in there. That said, in practice, especially if you're doing automated parameter tuning, it tends not to matter as much, because often the performance improvements we see are very large. And if you get an order of magnitude speed up, you can be confident that this is real and not just caused because of noise. If you get small performance improvements, as in so small that it could be just noise, then, well, you haven't really gotten any improvement in the first place. But often we do see very large improvements where there's essentially no question that it's noise, because it's so large that we can be confident to rule that out. But yes, this is actually one of the issues that you might be addressing in the exercise in a bit. Okay, I guess then let's break for coffee, and we'll come back. Yeah.